In the previous lecture, we had stopped at the point of spontaneous emission and stimulated emission. I had explained to you what is spontaneous emission and what is stimulated emission. So, in stimulated emission, the emission that comes out, the photons that are coming out after the particles have dropped down from E1 level to E0 level, those photons have the same properties as the incident photon. While in case of spontaneous emission, the photons that come out may not have the same properties as the incident photon. So, spontaneous emission anyways occurs because without any incident photon at all. Okay. So, now you have these two different types of photons which are coming out. In case of the stimulated emission, these photons are exactly like the incident photon. Not only is it the same wavelength as the incident photon, which is true even about the spontaneous emission, but it has the same coherence as it is coherent with the incident photon, and it has the same direction as the incident photon. So, in case of lasing action, this is what we are looking for. We are looking for stimulated emission, so that all the photons that come out or all the trains of light that come out, they are all coherent, monochromatic, and have all the properties of the incident photon. Okay. So, let me go further here. Here I want to introduce Einstein's coefficient A and B. These are very, very important coefficients. Let me go through some bit of the mathematics to know exactly where Einstein's coefficient fit in this case. So, you have these two level system E0 and E1. Let me just keep it here. Okay. This is E0, the lower energy level, and this is E1, the upper energy level, and you have a transition here. Okay. So, let N0 and N1 be the number density of particles in energy levels with energy E0 and E1. Then the upward transition is as follows. So, that means the number of particles, that is N0, that is the energy density of this level, the number of particles that go up to energy level E1 will be proportional obviously to the number of particles here. Okay. So, here you have N0. Okay. And then of course, because it is a induced transition, so you have U nu, which is the density of the radiation at a particular energy nu. Nu of course is the difference between E1 and E2. Okay. This is the difference. So, it has to be nu. So, the number of particles that go up are proportional to the number of particles in this level and also to the energy radiation that is coming in. Okay. Let me show it here. This is the energy photon that is coming in. Okay. So, this is U nu. So, that is that. Now, the number of stimulated emissions from level 1 to level 0. Okay, so, I said and B01 is, for the moment, think of it as a proportionality constant, B01. It is named as 01 because it is going from the 0 level to the first level. Okay. Now, the number of stimulated emissions from level 1 to level 0 is the following: N1 B10 U nu. That means the particle is dropping down from here to here, okay, and it is giving out some emission. Obviously, it will be dependent on the number of particles that have reached this level in the first place. So, you have N1 here. Okay. And then of course, the radiation that is coming out and the radiation that is incident, which is inducing it to come down here. So, it is proportional to the number here and it is proportional to the energy density at nu. Okay. And again you have a proportionality constant B10. B10 because it is dropping down from 1 to 0. Okay. we'll have to find out what B01 and B01 is equal to. That we'll find out later on. Now, the number of particles making spontaneous emissions per unit time per unit volume is also required. So, the particles that are here, some of them will come down not as stimulated emission, but as spontaneous emission. So, so the spontaneous emission will obviously depend only on the number of particles here. It does not depend on the energy u nu, because it is doing it spontaneously. There is no incident photon involved in it. So, it is proportional to N1, and this is the proportionality constant A10. 10 because it is going dropping down from energy 1 to energy 0. So, here I have written U nu is the energy density of the radiation at frequency nu, and B01 and B10 and A10 are the proportionality constant and are called Einstein's coefficient. So, A and B are the Einstein's coefficient. You can look at A and B as you know, a probability of particles going from E0 to E1, or particles that are coming down from 1 to 0, or you can look at it as a rate at which the particles are going from 0 to 1, and the rate at which the particles are coming down from 1 to 0. So, these are the Einstein's coefficient, and it's keep in mind that it is some kind of rate at which this is occurring. Now, at equilibrium what will happen? At equilibrium, N0 B01 U nu will be equal to N1 A10 plus N1 B10 to U. Basically, at equilibrium, all the particles in the density of particles in this 0 level will be equal to and the radiation will be equal to the stuff that is coming down from the top level. So, you have, it will be equal to the spontaneous plus the stimulated. This is what will happen at equilibrium. So, the number of particles here, okay, will depend on what is coming down from there and what is coming down from here. So, this is easy to understand. So, what I have done is just equated this part, this formula, to this plus this. Okay. So, again you just do a little bit of jugglery, you take all the u nu on one side, okay. Then you basically want to find out what is u nu, what is the energy density of radiation at frequency nu. That is what we are looking for. Okay. So, the radiation with frequency nu, and what is the density of that radiation. So, here if you do this bit of jugglery, u nu is equal to A10 upon N0 by N1 B10 minus B01 minus B10. Okay. So, this is kind of a formula for the radiation density at frequency nu. We have still got to find out what is A10, B01 and B01 and B10. Okay. So, let us see what these will work out to be. Here now, now we go back to the Boltzmann distribution. If you recollect, in the previous lecture I have spoken about the Boltzmann distribution. At equilibrium state, the energy levels are filled up according to the Boltzmann's distribution. So, N0, that is the lower level population density, will be equal to C e to the power E0 by kT. Okay. This is the lower level. At equilibrium, the energy density, number density, not the radiation density, the number density is equal to C e to the power minus E1 by kT. So, you divide this by this. So, you get N0 by N1 is equal to e to the power E1 minus E0 divided by kT. K is the Boltzmann's constant, if you remember, and T is the average temperature at that equilibrium point. Okay. So, this is equal to e to the power h nu by kT. Oh, now see, you have introduced the term nu, because you have E0 by E1 minus E0 is equal to nu, that is the frequency. So, if you substitute it back, substitute all this back into this equation, here you substitute it back here, what do you get? You get the value of u nu to be a0 e to the power kt h nu by kt, b01 and b10. Now, let us compare u nu with the Planck's formula. Planck's formula, which you had seen before, was P was proportional to the nu, the frequency, and the average temperature, and that is given by this big formula. If you see, basically u nu, which I am talking in terms of the radiation density, is same as P nu T, which is also a kind of radiation density. So, u nu and P can be equated to each other. Okay. So, you could write u nu, say, is equal to P nu T. Okay. So, you just put these two equations in place, and you will find that they turn out to be equal if B10 is equal to B01 equal to B. Okay. These two equations will be equivalent. If B01 and B10, we put it as B. Okay. And A10 by B will be equal to 8 pi h nu cube by c cube. Okay. So, if you use it in this equation, that is what you will find. So, we were trying to find out what is B. So, B01 and B10 turns out to be just B, they are both equal. That means, if you have a photon which is stimulating a particle to go up from level 0 to level 1, okay, the rate at which that is occurring, the rate of it falling down while it is being stimulated by another photon is the same. So, rate of going up and coming down is the same. So, only B is required as the Einstein coefficients, but A10, you could call it even A now, there is no A01, A10, the Einstein's coefficient, that is the stimulated emission rate. That is not equal to, okay, that is equal to A10 by B turns out to be, you have a known formula. Everything is known on the right hand side. Achha. So, you have this ratio of A10 by B equal to 8 pi h nu by c cube. Therefore, the rate of spontaneous emission is much more than the rate of stimulated emission. Okay, this is obviously a positive number if you take A10 and B on this side. So, rate of spontaneous emission is more than that of stimulated emission. That means, spontaneous emission is occurring more than stimulated emission, and that is not what we want. Our lasing action is we want more of stimulated emission, or we want to capture all the stimulated emission and keep the spontaneous emission aside, or let it be less and less. Okay. That is our whole idea. Now, how to achieve this? If you have an equilibrium system the way I have described, it does not happen. The spontaneous emission rate is faster and it will take over, and the stimulated emissions will just get lost in time. Now, there is a way forward. So, let us see what is the way forward. Now, consider, just for a moment, you consider the passage of light through a medium. So, you have this photon, it is going in through this medium, which has all these equilibrium number density n0 and n1, and it is going through this medium. And as it is going through this medium, it should be getting amplified as it goes through. Okay. So, as it is getting amplified, each of these photons are getting amplified, we would like to know what is the flux density of this radiation. We are all interested in the radiation, okay. We are not interested in the particles which are there, okay, unless in a secondary way. Okay. So, we want to know what is this spectral density of radiation at nu. So, consider now the spectral density of radiation at frequency nu is given by u nu, as I have explained in the previous slide. U nu changes due to the absorption by the atoms or molecules of the medium, and induced emissions by the atoms or molecules causes an increase in u nu. By the conservation law, induced transition can be written as follows. Okay. Oh, acha, there is this is a slide glitch maybe. I can put it as this is u nu. It came as a question mark there. This is u nu. Okay. So, u nu, as I am saying, it is the spectral density. Okay. Now, the rate at which it changes, or and by conservation law, the radiation that goes up and the radiation that is because of the stimulated and absorbed radiation should be constant. So, the rate, this rate is equal to h nu u nu, b is the Einstein's rate coefficient, and n1 is the number of particles in the lower level, and h nu is the radiation associated with that difference in energy level. So, obviously, it will be proportional to this and minus what is coming down. Okay. So, this is the one that is coming down, we are interested in this radiation, and this part is the one which is going up. Okay. So, we have to minus it. H nu, it is proportional to the energy, it is proportional to the incident photons u nu, it is and the proportionality constant is Einstein's coefficient, and of course, the number density in that level. So, if you just do that little bit of mathematics, it turns out to be h nu u nu b into n1 minus n0. Let us, for convenience, let alpha be h nu b n1 minus n0. Then you can write u nu as follows. Okay. So, I have introduced a new term. If you just plug in this alpha here, it gives you the value of u nu, but I have just introduced a new term, that is v. That is v here, which is the velocity in the direction in which all this flux is moving. I interchange the word flux and spectral energy density. They are both more or less the same. Now, I put in this velocity, and maybe this d u nu is slightly different from the other one. So, I will put a dash here. Okay. So, this u nu, but it is of course the rate at which that energy density is changing over time. And if I want to know what is the energy density along the z direction, I have introduced the term v, because these photons are actually travelling at a certain speed along this medium. Okay. So, if light is travelling in the z direction, I will assume that it is travelling in the z direction, and S is the energy flux density in that direction. Actually, S is just u nu, it is similar to u nu, but I have introduced the term S because it is u nu in a particular direction z. So, we have got to do a little bit of mathematical jugglery to come to certain conclusion. So, I can write ds by dt is equal to ds by dz into dz by dt, that means these two cancel each other. So, that becomes ds by dz into dz by dt is the velocity v. Okay. But from here what I see is, suppose this is ds by dt, okay, this ds by dt is equal to alpha v s. See, s is equal to u nu. Okay, it's just a bit of mathematics, you're putting this here, putting that there, a little bit of jugglery. So finally you come to ds by dt is equal to alpha v s. So ds by dz into v is equal to alpha s v. Cancel out the velocity from this side. If you take integral on both sides of this equation, you will come to this conclusion. Sz is equal to S0 e to the power alpha z. Just focus on this formula, on this equation Sz. So as you are going, as the photons are traveling along the z direction, you are exponentially e to the power alpha z, exponentially extracting energy from it. You are exponentially increasing the radiation that is coming out. Now the flux density decreases if alpha is negative, and the flux density increases exponentially if alpha is positive. Okay. So you see the value of alpha. Alpha is n1, it depends on n1 minus n0. So if n1 is less than n0, obviously alpha will be a negative number, and you will have flux density which is decreasing. So you have e to the power minus alpha z, okay, it will decrease. Now if n1 is greater than n0, okay, then alpha is a positive number. Okay, alpha is a positive number. Then your flux density will increase exponentially e to the power alpha z as it is moving along the z direction. So now n1 greater than n0 is called population inversion. So generally as you've seen before, okay, you have the maximum population here, you have a little less population here, you have a little more less population here. So if this is 0 and this is the 1 level, that we have seen as a equilibrium position of a medium, okay, at temperature T. So this has more and this has less. At equilibrium you don't get population inversion. You have to somehow make the population of this level more than the population of this level. Population of 1 has to be more than population of 0. In equilibrium it does not happen, that is what I am trying to say. That means by some means you have to get a population inversion in order to get lasing action, or in order to get more stimulated emission. So till now what have we seen? We have seen that spontaneous emission is more possible than stimulated emission. But we have to create a condition in this medium so that spontaneous emission becomes less and less and the stimulated emission becomes more and more. And stimulated emission will be more if n1 is greater than n0. So stimulated emission will be more if population inversion happens. Okay. So now what do? We have to get population inversion. Now population inversion will happen if there are 2 level, 3 level, 4 level systems. Okay. So I've just this is a 2 level system as we've been describing till now. Okay. Now there is a problem. We know we have to make n1 greater than n0. Okay. That is our aim. Now in this 2 level system, suppose you have so many particles in this lower level, n0 particles. Now with the incident photon you have managed to take half of them which have gone up here, half these number. Once half this number have gone up, that means the population in n1 is equal to the population in n0. Okay. So here, suppose here I have put, suppose there were 6 particles, 3 of them have gone up and 3 of them have remained below. So, you have the population of this energy 1 and population of this E 0 to be equal. Now, what happens then? If you see here, we have seen what happens when N1 is less than N0, N1 is greater than N0. Now, when N1 equals to N0, when N1 equals to N0, you have S is equal to S0 e to the power, alpha becomes 0, okay, e to the power 0. That means S is equal to S0. So, whatever is the population you started off with, maybe through spontaneous emission, that flux S0 is that initial flux. It has not amplified at all, and that is not what you want. You want it to amplify. So, having N1 equal to N0 is not your solution at all. But what can be done? What can be done? What can be done is the following. You do not take so the 2-level system is not working. This 2-level system is not working, because once this population becomes half, there is nothing more you can do. Okay. So, what do you do? So, what you have to do is think of a 3-level system or a 4-level system. Okay. Give it a thought, and in my next lecture, I will explain to you exactly how a 3-level system will work and how a 4-level system will work. Okay.